Hello and welcome to Autology, the podcast that brings you the latest insights into automotive technology. I'm your host, Rebecca Bellchambers, Senior Battery Research Analyst here at S&P Global Mobility, and I'm joined today by Adim, Battery Research Manager, and Hugo, Cruz, Principal Battery Research Analyst. In today's episode, we're going to be diving into one of the most critical and often debated topics in the electric vehicle space, battery pricing. It's well documented that the battery is the single most expensive component in an electric vehicle, and it's often referred to as the biggest pain point, not just for OEMs, but across the entire value chain. It has a direct impact on vehicle affordability, profitability, and ultimately the pace of EV adoption. But battery pricing is far from straightforward. While we've seen a long-term trend of cost reduction that's driven by scale, technology improvements, and vehicle supply chain optimization, recent years have introduced significant volatility. Raw material prices, particularly lithium, nickel, and cobalt, have fluctuated sharply, which is reshaping the cost structures and challenging the assumption that the prices will continue to fall at the same pace. At the same time, we're seeing a shift in how batteries are designed and manufactured, whether that's changes in chemistries, such as the growing adoption of LFP and future LMR variants, or structural innovations like cell-to-pack and cell-to-body architectures. All of these factors play over influencing the overall cost per kilowatt hour. So to help us understand all of these nuances in the battery price, the battery team have published the latest version of their battery pricing model called Battquant. So the first question I have today is for you, Ali. Could you maybe tell us a little bit more about the Battquant battery price model and maybe touching on the scope and the input parameters and some of the methodology behind this model?
Yes, absolutely. For Battquant model, we followed a bottom-up approach with a top-down fine-tuning layer. What that means in practice is that we started at the very base level. So from the commodity prices, you basically leverage the S&P Global internal services for historical battery metal prices, as well as the forecast metal prices, which then became the basis for the cathode active material price forecast model. Similarly, we built small cost models for each component that goes into the battery cell to cover the full bill of material. We typically start from the material prices, and then we add the processing and financial cost to estimate the cost of each component. For each model, we took into account also key variables like chemistry or cell design or production location or supply chain or supplier dynamics. Regarding the production costs, on the other hand, we layered in additional elements such as energy or labor, equipment, building costs, and so on. And at the end, like in order to have a comprehensive battery price, we had to add a layer of indirect financial cost elements such as research and development, selling, general and administration, or the profit margins. For all of these financial related elements, we leverage the financial statements of various listed companies. Once we had that full bottom-up cost structure, we didn't just stop there. So we validated and calibrated the model using real market data. So we conducted extensive interviews with industry players, and we also use historical price points from various sources to fine-tune the outputs. That top-down adjustment actually was really critical because it ensures that the model reflects the actual transactional prices, not just theoretical costs. So at the end result is a fairly flexible tool. We've essentially turned it into a simulator where users can select different configurations, so different chemistries, cell formats, production countries, and then see how those parameters translate into final battery prices. This service is available now to the battery domain subscribers on Autotech Insight. If the listeners are interested, they can reach out to us directly to get more information.
That's really helpful. Thank you, Ali. I think what stands out here is just how much detailed and grounded in the real world data that this model is. So that's really, really powerful. Maybe following on from that, Hugo, could you walk us through some of the key drivers that are contributing towards the battery cell cost structure?
Of course, Rebecca. Our model consists of three main buckets, which were already mentioned by Ali: materials, financial, and manufacturing costs. To explain the key drivers of the battery cost structure, I would like to reference the results of our model for two popular chemistries, NCM811 and LFP. According to our model, for 2025, the global average cost for NCM811 was $64 per kilowatt hour, and for LFP was $46 per kilowatt hour. It is widely known in the industry that materials account for the largest share of the battery cost. Depending on the cell design and the production location, the materials can account for 60 to 75% of the total cell cost. Of the materials, the cathode active material accounts for the biggest portion of the cell cost. The CAM share is notably higher in NCM811 when compared to LFP, and this is because of the raw materials used in it, nickel and cobalt. For high nickel NCM chemistries, the cathode active material accounts for almost half of the total cell cost, while for LFP, the cathode represents only around 1/4 of the total cell cost. Even if materials dominate the equation, the non-materials pieces, namely the manufacturing and financial cost, could still shape the competitiveness, especially when we consider the cell supplier scale, the production region, and even where the battery gets sold.
Thank you, Hugo. This highlights just how dominant the materials are, I guess, particularly the role of the cathode in driving the overall costs. So Ali, we see that lithium prices have been impacted recently. Can you give us some insights into maybe why that is?
Yeah, that's a great question. And honestly, there isn't just one single explanation. It's rather a combination of multiple factors playing out at the same time. So on the supply side, we've seen a few disruptions recently. For example, the CATL mine closure in China or the export restriction in Zimbabwe have tightened the supply, at least in the short term. That said, when we look at the broader picture, our colleagues in the market intelligence department still expect an overall supply surplus going into 2026. So structurally, the market is not necessarily tight. It's more about short-term imbalances rather than a fundamental shortage. And then there's another dimension, which is more on a financial side. What we have been hearing from the market is that some of the recent price movement is also linked to broader capital flows, with increased volatility in traditionally safe assets, such as bonds, for example. We're seeing some reallocation of funds into commodities and physical assets. And that shift has had a knock-on effect across multiple commodity markets, including the battery metals. So in a way, part of the recent price increase is not purely driven by supply-demand fundamentals, but also by investor behavior or market sentiment.
Yeah, thank you, Ali. That's really interesting. I think it's an important reminder that it's not always just the physical supply and demand that's driving this. It's also, factors like financial markets and sentiment that can really impact these prices quite considerably. And I think that links nicely into the kind of looking into the broader external pressures that are happening within the industry. So maybe if we take a look at this from a higher viewpoint, Ali, can you talk on some of the geopolitical factors that are having an impact on the battery cell price and other related components?
The most obvious example at the moment is the situation that we have in Middle East, in particular the closure of the Strait of Hormuz, that has had a severe impact on the global energy market. So I've seen energy prices skyrocketing, and that's important because batteries include some processes that are highly energy intensive. So we have, for instance, the battery cell manufacturing that includes some energy intensive processes like drying or dehumidifying, or the graphitization process in the graphite anode processing, or the calcination process in the cathode production. So you can imagine higher energy costs will affect all of these different levels across the value chain of the battery supply chain. That said, energy is just one single piece of the puzzle. So when you dig a bit deeper, you start to see much deeper set of supply chain impacts. For example, disruption in sulfuric acid supply, which is a key component in the refining of the metals such as nickel, cobalt, or copper, can create bottlenecks in the upstream of the value chain of some of the chemistries like NCM. And then when you also look at the petroleum derivatives, the high oil prices feed into the cost of the derivatives that are used in the battery production. And a good example is the needle coke, which is a key precursor for the synthetic graphite on the anode side. So what you're really seeing is a series of second and third order effect, almost hidden impacts that propagate across the entire supply chain. And when all of these factors come together, they tend to push the prices up, at least in the short term. Now, in terms of the outlook, we expect the impact for 2026 to be rather a temporary one than a structural shift in the cost structure. A lot will depend on how quickly the situation stabilizes. But even in a scenario where a conflict is resolved in a relatively short amount of time, it typically takes quite some time for the supply chains to normalize.
Yeah, it certainly does, and we've seen that in the past. And I think it's fascinating how interconnected all of these impacts are, and especially the second and third order effects that you mentioned, which aren't always immediately visible, but they clearly are having a real impact on the cost. So Hugo, over to you. Maybe you can take this a little bit further, and maybe you can talk on some of the protectionism and the regulations that are happening in Europe that might have an impact on the battery cost.
In the case of Europe, I do not see it as protectionism, but the European Union is shifting from an open market framework to one that also prioritizes autonomy. This is regarding battery industrialization. The Industrial Accelerator Act, IAA, seeks to boost manufacturing in the region. It will include a series of mechanisms for this, and maybe another podcast is required to explain the full scope. But in summary, for the battery sector, it includes 1. Support for strategic projects, and more importantly, incentives tied to local content. The goal is to build full and resilient battery value chains on European ground. According to our model, made in EU battery cells are currently more expensive than their Chinese counterparts. If we compare a high nickel ternary battery cell produced in either Hungary or Poland against China, the battery costs are 45% higher. And for countries like Germany, the difference goes above 60%. Why? Material sourcing and manufacturing costs are already higher than in China. We recently ran an analysis and found that a 50 kilowatt hour LFP battery pack manufactured in Europe, and let's say with European cells, could be between 700 and 800 euros more expensive than if it used Chinese cells. And this is including shipping and applicable tariffs. The incentives need to be good enough to bridge that gap. And there is an extra point that I would like to address. We should consider increasing compliance costs from recent regulatory changes, which include tracking emissions, recycled content mandates, life cycle traceability, and due diligence on materials. And let's just picture this. It will be additional IT infrastructure, supplier auditing and certification, and constrained sourcing. And this is in the case of recycling or restricted suppliers. Now, while these instruments are helping to close important information gaps across the battery supply chain, they will also come with a cost. And in the European context, we do expect these measures to push battery costs even higher, especially for those vehicles manufacturers that don't have the scale to spread or amortize those additional costs. So what we will see is a growing divergence where big players can absorb these pressures more efficiently, and smaller volume OEMs are likely to feel a larger impact in their sourced batteries.
Okay, that's great, thank you. I think that this really highlights the trade-off that Europe is facing between building a resilient localized supply chain and managing to remain cost competitive. Ali, how about Is there something similar going on in North America? Obviously, we've got the OBBA and the IRA, but how is this impacting the price of batteries in North America?
Yeah, so a lot is happening in North America on the policy side. So initially, the IRA introduced incentives across multiple levels of the value chain. On one side, you had up to $7,500 EV tax credits that were tied with local sourcing or sourcing from the free trade agreement countries. And on the other hand, you have some incentives that were targeting the suppliers through the advanced manufacturing tax credit, or 45X. What that effectively did was encourage localization, even if that meant using components that were more expensive compared to alternatives coming from China. But the key point here is that those higher costs were largely offset by the EV and production tax credits. Now the situation has vastly changed under the new administration. With the rollback of IRA, the consumer tax credits are no longer in place. But the advanced manufacturing tax credits under Article 45X remain in place under One Big Beautiful Bill, or OBBA. And that's quite important because those production tax credits are very generous and can reduce the price gap with China. However, even if producers were to fully forego the $35 per kilowatt hour production tax credit, there's still a noticeable price gap with the prices in China. And that is where the second layer of protectionism comes in, which is the tariffs. Especially under the current administration, we've seen an increase in the tariff levels on imported batteries from China. And those measures, to a large extent, close the gap between North American and Chinese prices. But of course, there's a trade-off here. While the tariffs and incentives together support local industry and improve the competitiveness on paper, the reality is that these additional costs don't just disappear. They're ultimately carried to the market. So in many cases, the end customer ends up paying more compared to the scenario where lower cost imported sales were freely available.
Yeah, thank you, Annie. I think it's really interesting to see how these policies can really reshape the cost landscape like that, not just necessarily the price. Particularly, when we look at how these incentives and tariffs are effectively rebalancing the competitiveness, even if the underlying cost structure does remain higher. So we can see that from the Battquant battery price model that the production costs differ per country, and we've already spoken about this. And the manufacturing costs are one of these big considerations. So maybe, Hugo, can you tell us why these manufacturing costs do differ and how this is included into the model?
Yes. I believe one of the capabilities of our model that was improved as compared to our previous models is the granular analysis of manufacturing cost on a country basis. We have already commented on the weight of materials in total battery cell cost, but the contribution of non-material costs is between 25 and 40% of the total battery cell cost. This still shapes supplier competitiveness, especially by country, scale, and cell design. In our model, we consider the following elements, which were already mentioned by Ali: labor, selling, general and administration, energy, research and development, and depreciation. This one includes both machinery and construction costs. To exemplify the differences between countries, we need to anchor to a cell design. Let's say a prismatic NCM 811 with a graphite anode. Let's start by analyzing the energy component. For European countries, the energy cost for producing 1 kilowatt hour of batteries can be more than double those of Chinese or American factories. In the case of United States, gigafactories benefit from the lowest industrial electricity prices. This is due to the country's electricity market structure. For machinery and construction costs, we found that the lowest costs are also in China, followed by South Korea. And this is because these countries are equipment manufacturing hubs and have a developed ecosystem of battery manufacturing. The capex in China, or capital expenditure, for a gigafactory producing high nickel NCM could be in the order of $40 million per gigawatt hour of capacity, while in the United States, it could be 3 times that. The differences are not only in the equipment, but also in the construction labor and regulatory burden. And talking about labor, this is the most influential factor in manufacturing costs. We found significant differences between countries. The lowest labor costs are also in China, which can be explained by high automation levels and national wages. The higher cost for labor are found in the US, closely followed by Germany, representing almost 6 times the labor cost of their Chinese equivalents for manufacturing 1 kilowatt hour of batteries. In the case of Europe, there are significant differences between countries. When we compare factories in Poland and Hungary, they could have labor cost of only 40% as compared to their counterparts in Germany.
Wow, I think that this is a really great illustration of just how much location of manufacturing plants really does matter. And not only just from a material standpoint, but also in terms of the structural cost advantages across, like as you mentioned, the energy and the labor and the capital. Thanks, Hugo. Okay, so let's move on now to talk a little bit about the BEV-ICE price parity. Ali, maybe you can touch on this. Where are we with this? Are we close to the $100 per kilowatt hour threshold that is so often regarded as the point of price parity?
Yeah, and that's a really interesting topic and one that industry has been watching quite closely for a long time. And we look at our battery price model in 2025, the LFP battery packs with cell to pack technology are already around $70 per kilowatt hour in China, well below the $100 per kilowatt hour threshold that traditionally has been regarded as a parity point. And in practice, also, we actually start seeing some parity emerging in some areas in the markets, like the A and B segment in China, for instance. However, in larger segments in China, like in C and D, there's still a gap in the price. And also in some regions, like in Europe and North America, the BEVs are significantly more expensive than internal combustion engine vehicles. And when you look at the battery pack prices, also we see that the prices for NCM packs are still above $130 or so per kilowatt hour. So we are not fully there yet. Especially in Europe, some of the OEMs are starting to produce LFP packs that can approach the $100 or $110 per kilowatt hour. But even with those LFP configuration, we see that the final price tag of the vehicle is significantly larger than internal combustion engine. So the way that I see it is that the $100 per kilowatt hour benchmark has been quite useful historically. So when you look at maybe 10 years ago, the battery prices were significantly higher, and this threshold gave a good reference point. And to be fair, it turned out to be surprisingly accurate as a rule of thumb. But now that we are close to that level, I think we need to start thinking in a more nuanced way. Because in reality, there's not just single parity point anymore. So first you have, for instance, the regional differences. The cost structure in China is fundamentally different from Europe and North America. So naturally, the battery price parity thresholds should be also different across these different regions. As I mentioned, in China, for instance, the $70 per kilowatt hour has been already achieved, and that's probably the parity point for smaller segments. But for larger segments like C and D, probably you need to reduce the battery pack price even further. And then you need to also take into account the segmentation effect. As I mentioned, in smaller vehicle segments with shorter driving ranges, it's much easier to reach the parity because the battery pack is usually smaller. That makes the pack more affordable. But in the larger segments, typically you need longer driving range, and as a result, you need a disproportionately larger battery pack that really increases the price further, making the parity point more difficult. And finally, I think it is important to remember that the battery is only one part of the story. Achieving the parity at the vehicle level depends also optimization of the rest of the electric powertrain um, and the overall vehicle cost.
Thank you, Ali. Yeah, I think you've made some really good points there. We can no longer sort of consider price parity as a single benchmark. It's much more scenario specific, dependent on whether what region we're looking at, what vehicle segment, and even the vehicle positioning. And so as we start to wrap this up, I think it's important that we discuss LFP a little bit. So currently the model is saying that the LFP price sits at around $45 to $50 per kilowatt hour. Is it possible for further price reductions in the future? Hugo, maybe you can touch on this.
Yeah, sure. Yes, our model indicates that the price sits at those levels, but there is an important consideration. China has market dominance in LFP battery manufacturing. Therefore, when we say that the global average is at those levels, pretty much we are speaking of Chinese prices. The short and medium term cost reductions in LFP batteries are expected in the manufacturing front. Maybe lower capital expenditures, both in machinery and infrastructure, less energy intensive processes, more factory automation, and lower levels of scraps. There could be also some marginal cost reductions in materials, probably by optimizing the upstream processing of battery grade materials, lithium, phosphate, and synthetic graphite. If we additionally need to consider something important. The LFP battery market is highly competitive, and the margin of several LFP cell suppliers is usually low due to this. So further reducing the average cost could be counterproductive for many LFP battery manufacturers. However, what we are witnessing right now is that LFP battery manufacturers are competing in another scenario. For EVs, this is performance. By improving their cell energy density and fast charging capabilities, they are making their batteries and vehicles more attractive to OEMs and end consumers. So beyond 2030, we are not really expecting continued cost reduction. Instead, what we expect is that average LFP cell prices will settle, hovering around the $38 to $41 range, with some sensitivity to commodity pricing cycles and the scale of the supplier manufacturer.
Okay, yeah, that's really interesting. Thank you, Hugo. So in order for us to really kind of experience significant reduction in price levels, is it fair to say, Ali, that we are maybe looking into new chemistries such as sodium ion to really reach those lower price levels?
Yeah, I agree. If we want to go below certain price thresholds, say below $40 per kilowatt hour, then new chemistries become quite inevitable. And today, sodium ion is probably the strongest candidate in that domain. And the core advantage is quite straightforward. So sodium ion battery replaces lithium, which is the one of the most expensive elements in the lithium ion battery cost structure. So structure, it gives a clear pathway to lower the material cost at least. But there's a big caveat here, which is the energy density. So sodium ion batteries today have a significantly lower energy density compared to lithium ion. And once you have a lower energy density, the cost per kilowatt hour goes up quite quickly because you need more materials, more volume. You need to process more materials and more volume. And all of that increases the price per kilowatt hour. So at this stage, even though the sodium ion has that theoretical cost advantage, the actual prices that we see in the market today are still significantly larger than LFP. Now, looking ahead, we do expect that that to change quite rapidly as the production volumes scale up. Based on our forecast, we see sodium ion battery reaching to the cost parity with LFP somewhere around early next decade. But to get there, there are still a few key challenges that need to be addressed. One of them is on the cathode side. Today's leading chemistries, such as layered metal oxides, such as NFM111, still rely on nickel. And given the relatively low energy density, you end up paying quite a lot of money for the nickel content, which kind of defeats the purpose. So reducing or eliminating nickel while maintaining the performance and energy density is going to be really critical in the price reduction of sodium-ion batteries. And then on the anode side, hard carbon is currently the main choice, and it is still quite early stage material. It has relatively low tap density, which impacts the overall volumetric energy density of the cell. And that's actually where we see a lot of room for improvement, probably more so than the cathode side. So as those material challenges are addressed, we expect the adoption to expand. And in the near term, the most natural fit is the energy storage systems. And we are already seeing that with some large-scale contracts being announced. In the EV space, we also expect gradual adoption, particularly for applications where energy density is less critical. And finally, I think there's a very important market dynamic here. Sodium-ion effectively acts as a hedge against the lithium prices. Based on our estimates, if the lithium prices rise above a certain threshold, I guess it's around $40 per kilogram LCE at the moment, you start to see immediate competitiveness between sodium-ion and LFP batteries. So what that means is that sodium-ion creates a kind of price ceiling for the lithium until the price parity is achieved. Whenever lithium becomes more expensive, some of the demand can shift towards sodium-ion, and then that relieves the pressure on the market, stabilize the prices. So overall, beyond just being a new chemistry, sodium-ion has the potential to play a broader role in making the entire battery market more resilient and less prone to kind of price spikes that we saw in the past, especially in 2022.
Thanks, Ali. Yeah, I think that's fascinating to see how various different chemistries can almost be hedged against each other to act as a price stabilizer. And I think as well, one of the biggest takeaways I have from this entire podcast is just it's very interesting to see how the conversation is shifting. We're not just talking about price reduction, but we're talking about performance improvements and, like I say, alternative chemistries and things like that. Thank you, you two. It's been a great podcast today. Unfortunately, that is all we have time for. So I'd like to say a big thank you to you both for joining Autology.
Thank you very much, Rebecca.
Thank you, Rebecca.
And thank you to all of our listeners for tuning in as well. We'd love to hear your thoughts on today's episode at our autology@spglobal.com email. And you can find out much more at autotechinsight.spglobal.com. Don't forget to hit all of the subscribe, follow and like buttons to stay on track with the latest Autology podcasts. And we look forward to you joining us again in the next episode. Bye for now.